This is the first video of a series covering the HyperMesh integrated Composite Stress Toolbox and its use cases. And in this video we are going to do some introduction to the Composite Stress Toolbox itself, starting out with a little bit of terminology. So first of all, when we talk about laminates, we also have to get plies into the picture, and plies are usually made up out of two or more constituent materials, typically fiber and matrix, like we see here on the right. And they get assigned a shape, an orientation, and a thickness in our model. And then when we put together several plies in a particular sequence, which we also call a stack, then we end up getting our laminate. Laminate is also what can be seen here in the bottom. And now when we have such laminate, then we can find particular areas that have a constant thickness and constant layup. And those areas are called zones. So there's basically two different approaches of modeling. The more traditional one is the zone-based, so where you really explicitly define a layup for each of the zones, and the more modern one, which is the ply-based one, which is more like the manufacturing process, where you really go define the plies, and then you basically, as a result, you will see what are the zones correspondingly. Then, looking at the integrated composite stress toolbox, we again see our four different terms: the material, the ply, the laminate, then the zones, or in the limit, one zone per element. And for all of those, we do have little tools that allow you to work through your process. So we have a built-in analysis engine. In the background, we are running classical laminate theory, first-order shear deformation theory, and we have a collection of first ply failure criteria available. Now, first thing is usually look at engineering constants, and you can do those for all of those different entities, so regardless of material, ply, laminate, zone, or element. Another use case is to put some load on the laminate or a zone or element. And when you do so, you might even want to combine that also with a set of first ply failure criteria. And then what you'll be able to do is calculating a load response. So that's a second kind of group of use cases. And then the last one is strength. So just looking at the laminates or elements and figuring out what would be the uniaxial loads that would cause this laminate to fail. And as a last overview slide, maybe here just a list of the supported profiles and the various entities. First of all, the solvers supported are OptiStruct, Nastran, and Abacus. And there's always a corresponding set of supported cards. I don't think it's necessary to read through all of them here. You can check your combinations if needed. When you're doing elemental analysis, it's important to note that it's not just supported for ply-based modeling, but also for zone-based properties. So if you happen to have the classic PComp or PComp-G, then you can also run analysis for load response or just the engineering constants on those ones. And if you do a load response with which is based on the results that you have already retrieved from your solver run, then right now that's supported in OptiStruct and Nastran for the file types listed out here. So OP2, H3D, H5, HT5, and XTV. Let's also take a look at the workflow. And on the left, we start with analysis entity-based one, which is the one available for all analysis types. So we start by creating an analysis and picking the type. Then we decide which entities, in our case plies, we want to analyze. And then you just right-click Run, and you get the results and can pick what you're most interested in at the moment. When we look at the right side, for the engineering constants, you can basically just pick the entities of interest straight away. Use the context menu and go to Analyze Engineering Constants, and you'll be ending up in the same analysis result viewer with all the same options that you have in the other workflow.